The Big Bang. This predominant cosmological theory about the beginning and early development of our universe suggests that approximately 13.8 billion years ago, all of space was contained in a single geometric point. That single point began to expand and eventually created galaxies, the stars, planets, and life. But our story of the universe begins about 13.79 billion years after the Big Bang, around 360 BCE.
The most important thing in everything is to start from the natural beginning.
The Greek philosopher Plato writes about the beginning and structure of the universe in a theoretical dialogue titled Timaeus. He writes,
"Was the world, I say, always in existence and without beginning?"
He then places Earth in the center of the universe and writes,
7 unequal circles, 3, Sun, Mercury, Venus, and the remaining 4, Moon, Saturn, Mars, Jupiter.
The universe to the Greeks was confined to what could be seen with the naked eye. Thus, why Plato's universe only contains the Earth, the Sun, the Moon, a few planets, and a rotating crystal sphere of background stars. Plato's worldview was important because it was the dominant view of the universe for the next 2,000 years. In the 16th century, Polish astronomer Nicholas Copernicus shattered the previous structure of the universe by publishing his book, 6 Books Concerning the Revolutions of the Heavenly Orbs, where he placed the sun at the center of the universe. We call this model the heliocentric universe, opposed to the Earth-centered or geocentric universe proposed by Plato and the Greeks. The heliocentric universe was actually first proposed 2,000 years before Copernicus by the Greek astronomer Aristarchus, but his theory was not widely accepted at the time. Copernicus cited Aristarchus as the ancient authority who advocated the positions of Earth and the Sun. However, Copernicus later crossed out this reference, leaving Aristarchus's theory unmentioned in the published book. Nevertheless, Copernicus's book was the first falling domino that started a cascade into scientific cosmology. After the Dutch invention of the telescope, Galileo Galilei was able to systematically observe the cosmos. He observed that the moon was spherical and had mountains and valleys, contrary to prior beliefs. Turning his telescope to Jupiter, Galileo observed 4 moons orbiting the gas giant, a phenomenon that could not exist in the geocentric model of the universe. However, it was Galileo's observations of Venus that proved the theory that Earth was not at the center of the universe. Using his telescope, Galileo found that Venus went through phases, just like our moon. The cause of these phases could only be explained by Venus orbiting the Sun, not the Earth. Galileo concluded that our solar system must be heliocentric, or sun-centered. In the late 1700s, Sir William Herschel attempted to measure straight-line distances to the stars. The resulting pattern he called the grindstone universe. Unfortunately, his methods failed to capture a true picture of the universe because he wrongly assumed that all the stars were of equal brightness and were at equal distances from each other. It wasn't until 1838 that Friedrich Bessel made the first direct measurement of the distance to a star, using what is known as the parallax method. If an observer moves from one position to another, a nearby object appears to change its position compared to the background of distant objects. In this case, the nearby fence appears to be moving faster than the mountains in the background. This phenomenon is called parallax. Parallax is how astronomers measure the distance to the closest stars. As the Earth orbits the Sun, astronomers can measure the parallax shift of a nearby star. When Earth is on one side of the Sun, the star will appear to be here compared to the background stars. 6 months later, the Earth will be on the other side of the Sun, and that same star will appear to be here compared to the background stars. Using the known distance from Earth to the Sun and the measured parallax angle, we can use trigonometry to calculate a star's distance. The further away the star, the smaller its parallax angle. Measuring very small parallax angles is difficult, even with sophisticated technology, so astronomers can only use the parallax method to determine the distances of about 200 stars closest to Earth. In the early 1900s, astronomer Henrietta Leavitt observed a number of variable stars called Cepheids. These giant stars vary in brightness over time at a regular rate. Since all the stars were in the same cluster, she reasoned they must all be approximately the same distance from Earth. Leavitt noticed the brighter the Cepheid, the longer the period of variability. Her observations became the period-luminosity relation. Shortly thereafter, Harlow Shapley was able to use Leavitt's period-luminosity relation to calculate the distances to stars in some nearby clusters. Since Shapley knew the period of variability of the stars in the clusters, he could calculate their absolute brightness. Knowing the absolute brightness, he then applied the inverse square law of light, which is that light becomes dimmer the further it travels, to calculate the distance to the cluster. Repeating this process with other clusters, Shapley was able to make a model of the size of the universe. Shapley's findings were at first widely debated because they increased the size of the universe tenfold. This debate was resolved by new scientific evidence. The key proponent was Edwin Hubble. Hubble researched what was then known as spiral nebulae, more specifically the Andromeda Nebula. Using the period-luminosity relationship of Cepheids, he was able to determine that Andromeda was about 1 million light-years away from Earth. Hubble went on to calculate the distances to other spiral nebulae, demonstrating that spiral nebulae are actually independent galaxies, like our Milky Way. This revelation changed the name of the Andromeda Nebula to the Andromeda Galaxy, filling the universe with innumerable galaxies and increasing the size of the universe another tenfold. On New Year's Day in 1925, at a meeting of the American Astronomical Society, Shapley's single galaxy theory was replaced by Hubble's new, larger universe composed of many galaxies. By the late 19th century, astronomers were using spectrometers to study detailed measurements of the light from stars. When starlight passes through a spectrometer, it separates into wavelengths that correspond to a specific location on the spectrum. Looking at the spectrum from distant galaxies, astronomers saw dark lines missing from the spectrum. These absorption lines were caused by the dust clouds in a galaxy absorbing those specific wavelengths of light. Using photographic exposures and plate measurements developed by Milton Humason, Hubble was able to study the spectral redshift of hundreds of galaxies. He noticed that the absorption lines were shifted towards the red end of the visible light spectrum compared to where they should have been according to lab experiments. To understand what this means, let's listen to a police siren. As a police car approaches us, we hear a high-pitched siren. As the police car passes, we hear a drop in pitch. This is because when the police car drives towards us, the sound waves in front of the car are compressed, producing a high-pitched sound. As the police car drives past us, the sound waves are stretched behind it, producing a lower-pitched sound. Light waves behave in a similar way that sound waves behave. As a galaxy moves away from us, the light coming from it is stretched, making it appear redder. Conversely, if the galaxy is moving towards us, the light coming from it is compressed, making it appear bluer. Hubble found that the farther away the galaxy is, the more redshifted it is, and the faster it is moving. If a galaxy is 2 times farther away, it is moving 2 times faster and is 2 times more redshifted. If it is 3 times farther away, it is moving 3 times faster and is 3 times more redshifted, and so on. When astronomers say the universe is expanding, they mean that space itself is expanding, not the galaxies that lie within space. To understand this, picture a loaf of raisin bread. In this analogy, the raisins are the galaxies and the dough is space. As the bread is baking, the dough expands, and the distance between the raisins gets larger and larger. However, the raisins themselves do not expand. Likewise, as the universe expands, the distance between galaxies increases, but the galaxies themselves do not change. Since we see almost all galaxies moving away from us, some people infer that we lie at the center of the universe. However, there is nothing special about our location in the universe. Observers in distant galaxies would also see all the other galaxies moving away from them, just as we see galaxies moving away from us. If the universe is expanding, then it would be logical to assume that at some point in its past it was smaller and in a centralized location. This idea brings us back to the Big Bang. Contrary to the name, the Big Bang was not an explosion. It was the rapid expansion of space itself. The universe started very, very small, and then grew to the size of a soccer ball in a very small amount of time. This period was called inflation. Just after inflation, quarks and antiquarks flashed into existence out of energy. Quarks are subatomic particles that make up protons and neutrons. In particle physics, antimatter has all the same properties of regular matter, but with opposite charges. For example, an electron is made of matter and is negatively charged. The antimatter equivalent of an electron is the positron. A positron has all the same properties, such as size and mass, but is positively charged. When matter and antimatter collide, they annihilate each other and are converted back into energy. During this time, there was battle between matter and antimatter, simultaneously being created and destroyed in gigantic bursts of energy. By random chance, there were 1 billion antimatter for every 1,000,000,001 matter. That 1/1000th of the original matter left over from this cataclysm is what makes up all that you can see today. Galaxies, stars, planets, and even us. We are that leftover 1/100000th. As the universe expanded, the temperature decreased, and the all-in-one grand unified force of the universe split into separate forces, like gravity and electromagnetism. This caused quarks to form into protons and neutrons. Now, at 1 second old, the universe has grown to 100 billion kilometers, cooled to 10 billion degrees Celsius, and the first element, hydrogen formed. However, with so much matter in such a small space, light could not penetrate the hydrogen gas. Only after a couple 100,000 years, the hydrogen gas clumped together, allowing light to pass through the clouds. Finally, there was light. If the universe began with the Big Bang, we should be able to detect afterglow of the rapid expansion of the early universe. In 1964, we did. By accident. Arno Penzias and Robert Wilson at Bell Telephone Laboratories detected a buzz in the background of their radio signal. After trying repeatedly to eliminate the buzz, they discovered that it was coming from the universe itself. Energy from the Big Bang was originally in the form of super-energetic gamma rays. As the universe expanded and cooled, these gamma rays were stretched or redshifted all the way to microwaves. Today we call this energy the cosmic microwave background radiation, or CMB. To listen to the Big Bang yourself, simply turn on a TV or radio to a channel with static. 1% of the snow or noise on a TV or radio comes from the Big Bang itself. The discovery of CMB tipped the balance of evidence in favor of the Big Bang. Today, it is the most widely accepted scientific model about the beginning and evolution of the universe. The CMB tells us about the shape or curvature of the universe. Curvature is how much a geometric object deviates from being flat. It is hard to imagine curvature in 3 dimensions, so we will look at it in 2 dimensions. To look at the curvature of our universe in 2 dimensions, we need to examine a cross-section or slice of it. The universe has 3 logical shapes. The first is the surface of a sphere. This is called positive curvature. The second is a negative curvature, like the surface of a saddle. The final possibility is a plane with no curvature at all. The curvature of the universe dictates how light will travel through it. If the universe has positive curvature, like the surface of a sphere, then 2 straight beams of light will converge, or come together over time. Conversely, if the universe has negative curvature, like a saddle, 2 straight beams of light will diverge, or split apart over time. If the universe is flat, like a plane, 2 straight beams of light remain parallel forever. In June 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. The mission of this spacecraft was to detect fluctuations in temperature of the early universe. In this image, the fluctuations appear as different colored spots. From the WMAP data, scientists can say with 99.6% certainty that the universe is flat. Knowing the curvature of the universe tells us if and how the universe will end. Scientists have determined that the universe is expanding, and the rate of expansion is accelerating. In the past, astronomers thought the universe acted like a ball thrown up in the air. It goes up, and it comes back down. The universe would expand to a point, and then gravity would pull it back together. However, observations show the universe is more like throwing the ball up and watching it move faster and faster away from you. What is causing this acceleration? The short answer? We don't know for sure, but scientists have an idea, and they call that idea dark energy. The presence of dark energy leads us to three possible fates for the universe. The first possibility is the Big Crunch or the Big Bounce. This theory proposes that the universe will expand to a point, stop, and recollapse, crushing everything back into a single point. The Big Bounce suggests that after the collapse, the universe will bounce back into a new Big Bang. In this theory, there is an infinite number of deaths and rebirths of the universe. No information, nor memory, nor glimmer from the previous universe propagates or makes its way through the void into the next universe. The second theory is the Big Rip. Galaxies are moving away from each other because the space between them is expanding. The space within galaxies is expanding as well, but here there is enough gravity to keep the galaxy together. In the Big Rip scenario, the rate of expansion reaches the point where gravity can't overcome the expansion and galaxies are ripped apart. At first, only galaxies are ripped apart. Then, objects like stars and planets are ripped apart as well. By this time, all of space is expanding faster than the speed of light, and atoms themselves rip apart. After that, no particle will ever be able to interact with any other particle in this dark and timeless universe. The last scenario is the Big Freeze. The Big Freeze theory is much like the Big Rip theory with one major change. In the Big Freeze theory, matter stays together, but the expansion causes the universe to cool down until the last atoms radiate away their energy while space expands into nothingness forever. Because our universe is most likely a flat, accelerating universe, cosmologists think the most likely fate is the Big Freeze. Take comfort in knowing that it will take trillions of years for this to happen. This leaves plenty of time for us to expand our minds, explore the cosmos, and learn more about the secrets of cosmology.